Hi there. In this video, we're going to be looking at evaluating line integrals using arc length and parametric equations. We saw in previous videos that a line integral is some function integrated along some curve. And we saw that we can represent this as the sum of two different curves, or the sum of two different functions, p dx and q dy. The question at this stage is, instead of representing this integral on the left-hand side, ft ds, and evaluating it as two other different functions, can we just evaluate it directly? Well, we can do that if we represent ds in terms of the variables that can be integrated, specifically dx or dy. So basically what we do is we represent ds in terms of dx. Is there a way to do that? Well, it's covered quite extensively in single variable calculus, and the technique to do that is just to think about the theorem of Pythagoras. If you have a function and we have some length here, delta s, then we can just express that in terms of delta y and delta x. So by the theorem of Pythagoras, delta s squared is just delta x squared plus delta y squared. Then if we divide everything by delta x, then we get delta s divided by delta x squared equal to 1 plus delta y over delta x squared. So if we let delta x approach 0, then the deltas become d. Delta s, delta x becomes ds dx. So we get ds dx squared equal to 1 plus dy dx squared. So all we do is solve for ds. So that means that ds dx is equal to the square root of 1 plus dy dx squared. And of course, ds is just the previous term multiplied by dx. So if we substitute this into our line integral, what we're going to be left with is that I, which is initially equal to the function times ds, so this ds gets replaced by our integral, which is now in terms of dx. So it becomes ft multiplied by 1 plus dy dx squared times dx. We can illustrate this through a simple example. We can have some function that we want to evaluate the line integral for, and that could be between 2 points O and A, and the function that we're evaluating is 4x plus 3xy times ds. So this 4x plus 3y is our function. So we are evaluating this line integral between 2 points, and those 2 points are the origin and some other point A, where A is the coordinates 1, 2. And joining OA is a straight line. So what this tells us is that this curve is actually the line y is equal to 2x. So y is just double the value of x. The intercept is the point of origin, and it's a straight line, so yeah, y is equal to 2x. So that means that dy dx is equal to 2, and of course if we square this, dy dx squared, then we just get 4. So we want square root of 1 plus dy dx squared. So if we do that, So 1 plus dy dx squared is simply equal to 1 plus 4, which is equal to 5. So our initial integral required 4x plus 3xy. So if we take that down, what we're going to be left with is that I is equal to the integral from 0 to 1. That's our integration boundaries. And this function 4x plus 3xy. So y is equal to 2x. So we have to substitute that in. So x times x is x squared, and 3 times 2 is 6. So 3xy just becomes 3 times x times 2x, which is equal to 6x squared. Sorry. So that's equal to 6x squared. So if we put that into our integral, that becomes 6x squared. And also, we cannot forget that we have to put in our ds, and our ds is equal to the square root of this. Sorry, I kind of just let it get all a bit muddled here. Yeah, so I will just bring it below. Yeah, so that's our function, and we have to have the square root of 1 plus dy dx squared, and that's the square root of 5. And of course multiplied by dx. So we have our function, and we have ds. So it's just a simple matter to evaluate this integral. So this root 5, that's just a constant. We can bring it to the front. The integral of x is x squared, and we need to multiply it by something to get 4, and that's going to be 2. Integral of x squared is x cubed, so 3 times something needs to give us 6, and that number would be 2. And we're integrating this between 0 and 1. So the integral of just substituting 1 in, it's just going to give us just the number in front of the x. So 2 plus 2 is 4. So 4 times root 5 is just 4 root 5. Okay, so that's how we would do an example in which we substituted ds using arc length, the equation for arc length, that is, and it enabled us to find the integral directly without having to substitute pdx plus udy. So we can also evaluate the line integral directly if we look at parametric equations. So let's just write our line integral again. So it's the integral along some curve of some function acting along a certain arc of a curve. And instead of integrating with x as we had done using arc length, we can now perhaps use another variable, for example, t, dt. Well, it could be anything. So once again, we could look at the theorem of Pythagoras. Delta s squared is equal to delta x squared plus delta y squared. And all we'll do is simply just divide by the variable that we want to now look at it in terms of, in this case, t. We'll divide this entire equation by delta t, of course, squared. Delta t squared. So we just solve for ds as we had done previously, but before that we let delta t approach 0. So delta s delta t becomes ds dt. So if we do that, we solve for ds, what we get is that ds is equal to the square root of dx dt squared plus dy dt squared multiplied by dx. So our line integral now becomes substituted in for ds. So that would be the function times ds, and ds is everything that I've just underlined. So it's the square root of dx dt squared plus dy dt squared times dt. So we can illustrate this through a simple numeric example, and that would be to integrate the line integral. I is equal to the integral of some curve of the function 4xy ds, and we would need some equations. We would need x to be in terms of t and also y to be some equation of t. So we could say that x is equal to sine t and y is equal to cos t. These are just parametric equations. We have x and y in terms of the other variable t. So we're expressing ds in terms of t. So to use our equation that we have derived, we would need to find dx dt, dy dt, square both of them, take the square root, substitute it into this integral, and then evaluate the integral. Perhaps we should also mention that this curve requires t to go from 0 to pi over 4. So this is our integration boundaries. We would need to find dx dt. So dx dt is, let me just write it like this. Dx dt is equal to cos of t, derivative of sine is cos. Similarly, the derivative of y, so dy dt, is equal to minus sine t. Derivative of cos is minus sine. So we need to square dx dt and dy dt. And when we do that, we get dx dt squared simply equal to cos squared t, and dy dt squared equal to sine squared t. And of course, the equation requires us to add both of them and take the square root of it. So cos squared t plus sine squared t is simply going to give us 1 through the trigonometric identity. And if we do that, okay, let's just write it first. So dx dt squared plus dy dt squared is equal to cos squared t plus sine squared t, which is equal to 1. So what that means is that ds is equal to dt. What is ds equal to? We can see from our equation that ds is equal to the square root of dx dt squared plus dy dt squared times, sorry, this should be dt. Well, we have just shown that this dx dt squared plus dy dt squared is equal to 1. And of course, the square root of 1 is just 1. So that means that ds is equal to dt. So all that's required for us now to do is just to substitute everything into our line integral, which we will now do. And if we do that, we see that I, our line integral, is equal to, firstly, our integration boundaries is from 0 to pi over 4, which has been defined as part of the example that we're solving. And 4 times xy. 4 times xy is just 4 times sine t x times cos t, which is y. And of course, ds we saw was equal to dt, so we just substitute in dt. If we look at this term inside the integral, we see that it actually very similar, or it very closely matches our trig identity. And that identity that we're talking about is that sine of 2a is equal to 2 sine a cos a. So we would now put that into our integral. So what this means is that I now becomes 2 times the integral from 0 to pi over 4 of 2 sine 2 theta. Sorry, there should not be a 2 there in front. We've already put it in front of the integral. It becomes sine of 2t dt. So all that's left is to evaluate the integral. The integral of sine is minus cos. So we'll have a minus cos 2t. And since we have a function inside a function, we have to somehow cater for this 2t, and the integral of this 2t is half. If you differentiate this, the derivative of cos is sine, and the derivative of this 2t is just 2, and this 2 times the half gives us 1. So that caters for the 1 in front of the sine. So 2 times pi over 2 is, 2 times pi over 4 is pi over 2, and cos of pi over 2 is simply equal to 1. Sorry, my apologies. Cos of pi over 2 is equal to 0. So this first term basically disappears from the integral. And then we have cos of 0. Cos of 0 is 1. So minus half times 1 is minus half. And there's already, maybe we should just expand it out. So we have 0 minus a half. And this will leave us with 1. So the whole purpose of this example was to illustrate how we can convert our line integral ds to be in terms of some other variable, and the example used was t. So the whole purpose of this video in general was to evaluate the line integral to be in terms of other variables such as dx and dt, such that we don't have to use some other form of the integral, for example, pdx plus qdy.